So let me continue with the section short spec. In this slide, we are going to learn about Dijkstra, Bellman port, and DAG. So we are going to learn what is weighted graph, and we will learn about the shortest path algorithm and some example with the additional algorithm. Shortest path. What is shortest path? In the shortest path, we are going to use graph. And in the graph, we have weighted graph. The weighted graph means each of the edge, this is the edge, this is the edge, has an associated numerical value. So we call this is the weight of the edge. So this is the weight, this is the weight, this is the weight, and so on. Each weight may represent distance or cost or anything. So for example, in the flight route graph, so if you already know, this is a flight route. This is from San Francisco to Los Angeles. Then this might represent the distance in miles. So I can know the distance from San Francisco to Los Angeles is 337 miles. We are going to look at the shortest path. Okay, so I think many of the team would like to use the shortest path. Okay. Given a weighted graph and two vertices, this is U and P. So we want to find a path of minimum total width. A minimum total width means if I want to go from Honolulu to this PVD, I can go from here to here, or I can go from here to here. I can go from here to here. I can go from here, here. I can go using this path, and I can go using this path. So there are many options. So we are going to find the minimum total width between U and V. And we are going to calculate what path is the most minimum value. So we are going to find the length of a path. So the length is the sum of the width of each edge. For example, we are going to find the short path between Providence and Honolulu. So we want to find the distance from here to Honolulu. There are some other applications, for example, the internet packets routing. So if we want to find what is the best way for the internet packets, or we want to find the flight reservation like this one, or we want to find the driving direction, we use the short path. There are some properties of the shortest path. So the property one, a subpath of a shortest path is itself a shortest path. Okay. What does it mean? Subpath. If we know that this is the shortest path, okay. So let's say this is the shortest path. The shortest path is from A and L, X and L, and then go to LAX, and then go to ORD, and then go to PVD. Okay. So what is the subpath? The subpath is, it is from A and L to LAX. So this is one of the subpath. There might be another subpath from LAX to ORD. So this is also a subpath. And we can have also another subpath, which is ORD to PVD. It means this is subpath between two nodes. So this is subpath between two nodes. We can also have another subpath. For example, I want to go from Honolulu to ORD. So this is another subpath. Okay. Property 2. There is a tree of shortest paths from a start vertex to all other vertices. What is tree? We learn from the graph and we learn also about tree. If we have a tree, it means we also look at a kind of simple path. So if we know that there is a shortest path, there is a shortest path from Honolulu to Providence. Okay. So there is a tree. So this is one of the three. So for example, tree of shortest path from Providence. So this is a tree from Providence to Honolulu. So there are many shortest path algorithms, and we are going to learn only the basic algorithms. So we are going to learn about the Dijkstra, which is the shortest path from one node to all nodes, and Bell-Mumford, which is the shortest path from one node to all nodes, negative edges allowed. Because in Dijkstra algorithm, the negative edges are not allowed. Okay. Floyd-Warshall. We are going to find the shortest path between all pairs of vertices, negative edges allowed. Okay, so we are going to look at those three algorithms. The first is Dijkstra. The Dijkstra algorithm, it is a distance between one vertex V from a vertex S. Okay. Then we are going to find the length. What is length? We already know from the previous example. It is the summation of the weighted edges. It is the summation of the weighted edges. If we do the summation, then we can get the length. So the Dijkstra will find the distance, which is the length of the shortest path between S and B. The Dijkstra algorithm computes the distance of all the vertices from a given start vertex. Okay, we are going to find the all vertices, not only one. So the assumption is the graph is connected. You still remember what is connected graph? And every of the node is connected. Then, yeah, this is the assumption. The edges are undirected. So there is no direction. There is no direction. Okay. The assumption is undirected. And the edge weights are non-negative. What is the meaning by non-negative? It is positive. Okay. We call it non-negative because usually we include 0. So if we include 0, then it is non-negative. In the concept of Dijkstra, we grow a cloud of vertices beginning with S and eventually covering all the vertices. So let's see later what is the meaning by cloud. We start with its vertex V, a label dV representing the distance of P from S in the subgraph. Okay, so if we have graph, we will look for every possible subgraph consisting of the cloud and its adjacent vertices. So for every step, we are going to add the vertex to the cloud and outside the cloud with the label distance d. And then we update the labels of the vertices adjacent to you. Maybe it's better to see the example. Okay. There is one concept in the Dijkstra, we call it edge relaxation. The edge relaxation means if we have an edge u z, so from u to z. So u is the vertex most recently added to the cloud. So it means u is the vertex that recently has been calculated. So we are going to check z, which is not the cloud, not in the cloud. So the relaxation means the relaxation of HE updates the distance z as follows. We can do the calculation to z. The distance to z is the minimum of the dz. So the minimum of the starting point to z. And we want to find the minimum from the distance s to u plus the distance from u to z. Then we can do, let's say this one. The distance from S to Z is 75. But I want to check the distance from S to U. Okay, the distance from S to U is 50. And let's check the distance from U to Z. So it is 10. To 60. So this is the meaning by edge relaxation. Now let's look at the example. I have this kind of graph. So this graph start from A and we have B, C, D, E, F, and we want to set A as the origin. So the starting point is A. And then let's see, this is the weighted edge. So the weighted edge means from A to B, we have the value 8. From A to D, we have the value 4. From A to C, we have the value 2. From B to E, we have the value 2. From C to E, we have the value 3. From C to F, we have value 9. And from D to F, we have value 5. Then we are going to check the dz, or the distance from the origin. Let's say this is the starting point to all the vertices. So we are going to check from A to B, C, D, E, and F. From A to B, what is it? From A to B, we know from this x, the distance is 8. From A to C, we know the distance is 2. From A to D, we know the distance is 4. What about the distance from A to E? Okay, so there is no direct edge. Because there is no direct edge, we need to calculate maybe from B, from C, from D. So we will calculate it later. Then the distance from A to E is infinite for the first time. And the distance from A to F, it is infinite for the first time. Then we can check what is the minimum between dz and du plus width E. Because every point here start from A, and it is the same. It is the same. It is the same. What is the minimum? The minimum is 2. So we set C as the next node for our possible calculation. Now we start from C. From C, okay, so we say that we have a path from A to C. Now let's update the distance to B. If we want to go from A to B, if we go from A to B directly, the distance is 8. This is the original. But what if we want to go from C? Okay, because now we are on the C. If we go from A to B via C, then it is 2 plus 7. So du plus width E is 9. In this case, we are still not finding the square of square, we just find the distance. Because we are already chose C, then dz is 2 and the du plus width E is 2. What about T? T, we can see that the edge from A to D is 4. But if we want to go from A to D via C, so the edge is 2 plus 1. And du plus width E, it means from C, if we want to go to D, there will be additional 1. So the distance is 3. But the original distance from A is 4. Okay, then we can say that this is the du plus width E. Now we need to check what is the minimum. Let's go to this B. The minimum at this moment, we can check the C. Okay. C, we can go to E. Okay. We can go to E. We can go to E via C. Then it is 2 plus 3. Then it equals 5. We can go to F. We can go to F via C. So it is 2 plus 9. Then it is 11. Now we need to check again the minimum. Okay. At first, we select what is the minimum of B. The minimum of B is 8. What is the minimum? Because we are now in C, so we do not check this one. What is the minimum from D? The minimum is 3. What is the minimum from E? It is 5. What is the minimum of F? It is 11. Then we choose the most minimum, which is D. So we choose the next point is D. Then we have the shortest path from A to C is 2. The shortest path from A to D is 3. Again, we will check the other possible root, the other possible path. Now we still have the A and B like this one because there is no path from D to B. Okay, there is no path from D to B. What about D to E? D to E. So at the previous one, we have the distance equals to 5. So we set the A to E is 5 because we are going from A to C to E. But is there any path from A to D to E? There is no path. Okay. What about A to D to F? Okay, we have A to D, which is via C. This is we know already 3, and then we can go from D to F, which is 5. So 3 plus 5, it is 8. Now we can check what is the minimum. 8 and 9. So the minimum is 8. This is 2 because we already in here. We do not consider this one. We already here. We do not consider this one. And then this is 5. And this is also 8. Then we choose the minimum, which is 5. Now we are in the node E. So now we are in the node E. So we calculate again. If we are in the E, we can calculate the other possible edge relaxation. What is it? From E, we can calculate to B. What is it? We have the 2 plus 3 plus 2. Okay. 2 plus 3 plus 2 is 7. The original distance is 8. And then we already visit C, we already visit D, we already visit E, and now let's check F. Is there any path from E to F? No. And the distance, the previous distance is 7. The previous distance is 8. And for B, we need to check the minimum. The minimum between 8 and 7, it is 7. So we choose B for the next node. We choose B for the next node. And then in B, we cannot go to any other node. We cannot go to F because there is no direct edge to F. Then we choose F at the last one. Then this is the minimum distance from A to all other nodes, to all other vertices. So if you are looking if you make the team project with Dijkstra algorithm, when you say that you want to find the shortest path, it means you will find the shortest path from starting point to all the vertices. Okay. So this is the algorithm given by the author about the shortest path. And in this book, they use the priority queue. So the input is a weighted graph G with non-negative edge width and a distinguished vertex S of G. And the output will be the length of a shortest path from S to V for its vertex V of Q. So the initial value, the distance S will be 0. Okay, the distance S will be 0 means if we start from A, of course, it is 0. And the distance to V, the distance from A to V, the distance S to V it will be infinite for the first time. This is just for initial value. So it is for the vertex which is not equal to S. So A means the starting point. The starting point of S is 0 for the distance. And we can use the priority queue for all the vertices. And if the queue is not empty, then we will check. Value returned by the queue remove minimum. So if the value is minimum, then we will remove it. And then for every vertex V adjacent to U, such that V is in the queue, then let's do the relaxation. The relaxation means this is the formula. We want to find the minimum between the du plus weight of u, comma v. If the du plus w u, comma v is less than the dv, then let the dv equals to du plus w u, comma v. Okay, so we already learned this one about the relaxation. Using this formula, we will get all the distance from the start to V. This is the analysis of the Dijkstra. Because it is graph, so we want to find the all incident edges. All incident edges means we want to find this edge. We want to find these edges. We want to find these edges. And we are going to do the label operation. It means we are going to set and get. So it is O degree of Z. And set and get label, it is 1. If you still remember the priority queue, we use the priority queue. So the priority queue, each vertex is inserted one into and remove one from the priority queue. So if it is 1 and 1, then yeah, we can have the O log n for the insertion and removal. And if it is, we have the W times, then each key takes O log. So the Dijkstra will check our every node and M, which is edges, log n. Provided the graph is represented by adjacency lists or map structure. So we need to know the adjacency list. Then this is the property of the graph. At the end, you can see that the running time of the Dijkstra will be OM log n, since the graph is connected. Okay, I think this is the time. So thank you very much. Please check tomorrow. I will give you assignment. Please check on the class about the assignment. Thank you very much for attending the class. Hello,